here's a question. Given a space unimodular lattices in Rd, the Euclidean space of dimension d, and the unimodular here basically means the co-volume of those lattices are all equal to 1. And you equip this space with the topology, the subspace topology of this homogeneous space SLDR mod SLDZ. Remember, this is a homogeneous space consisting of right cosets of SLDZ in SLDR. And now the question is how to tell when this space is compact. And it's easy to see that one necessary condition for this space to be compact is that this space is a closed subset when you consider its topology as a subspace topology of this. And there's another condition, which is essentially the Maa-ler's compactness criterion that we are going to introduce today, saying that this space of unimodular lattice has to be kind of uniformly discrete. You know, every lattice is discrete. And when it becomes uniformly discrete, when the space of those lattices become uniformly discrete, then the closedness will imply the compactness. Hey guys, today we are going to talk about the famous Maa-ler's criterion for the compactness of in the space of lattices. But before that, let's briefly recall some definitions. Recall that a lattice lambda in Rd, where d is an integer, is defined to be the z-span of some linearly independent vectors in Rd. Specifically, it is a z-linear combination of those terms, where those epsilon sub i's form a basis of Rd, and n sub d's are integers. And this lattice is called unimodular if you consider the quotient of Rd by lambda. This space has a translation invariant measure with respect to Rd, has an Rd translation invariant probability measure. Say mu. And remember, this means this mu of a subset A in this quotient is same as rho of A plus x for all x vector s in Rd. And that's the meaning of unimodular. And that is the meaning of being unimodular. Or equivalently, we say this lambda has covolume 1. And this mu should satisfy that mu of this whole quotient space should be equal to 1. And that's the meaning of unimodular. And notice that in this particular situation, when the lattice is just in RD, this also means this measure mu is actually induced from the Lebesgue measure on RD. And being unimodular here simply means that if you take the determinant of this matrix, the matrix whose column vectors are epsilon 1 through epsilon d, where each epsilon I is written as a column vector, say a sub I1 all the way through a sub id, using the standard basis E1 through ED. Remember, E sub I is the column vector where the S entry is 1 while other entries are 0. Here, so the being unimodular here simply means the determinant of this guy is equal to 1. And sometimes we also call this property of measure 1 the covolume of lambda being 1 in RD. Or in other words, we may say lambda has covolume 1. There is a fact saying that any unimodular lattice takes the form lambda sub g equal to the inverse ZD for some g in SLDR. And there's another fact saying that SLDZ always preserves the lattice lambda in RD, namely G inverse lambda is equal to lambda for any G in SLDZ. And it follows from those two facts that you have the following 1-1 correspondence between the right coset space SLDR mod SLDZ and the unimodular lattices in RD. And it is given by sending the coset SLDZ .g to G inverse .zd, which is by our notation above lambda sub g. And by the first fact we list above, this is clearly surjective. And now let's check it is well defined and injective. So well-definedness and injectivity. If SLDZ.G1 is same as SLDZ.G2, then it is equivalent by definition by G2 G1 inverse belonging to SLDZ. And you know by the fact 2 above that this is same as saying G2 G1 inverse ZD is same as ZD. And this, furthermore, is same as G1 inverse ZD is same as G2 inverse ZD, which is lambda sub G1 same as lambda sub G2. This verifies the well-definedness as well as the injectivity. And this establishes the identification between this homogeneous space and the unimodular lattice in RD. Now at this point, I'd like to make a remark. Notice at this point, we are sending this radical set to G inverse ZD. And you might be curious to ask, can we replace this G inverse by G? And the answer is no. So indeed, if we use the map SLDZ.Z map to GZD instead of G inverse D, then G1 dz being equal to GZD, which is equivalent to G1 G2 G1 inverse D2 in SLDZ is no longer equivalent to G2 G1 inverse being in SLZD. And you know that this last term is same as G1 ZD being equal to G2 Z, G1 inverse ZD being equal to G2 inverse ZD. And we just proved that this guy is equivalent to SL dz G1 being equal to SL dz dot G2. After all, this tells you that this guy and this guy are not equivalent. So we cannot use this map instead. We have to take G inverse. Some of you might be curious at why those two things are not equivalent. I believe you should be able to come up with an example on your own, but I will tell you anyway. Indeed, you can observe that the situation here is same as saying that you have matrix A and matrix B. The product matrix AB being in this SLDZ is now seen as BA being in SLDZ. Now we try to create a concrete example. So what you want to do is that you want the matrices A and B are both in SLDR, but at the same time, well, you want A times B is in SLDR, SLDZ. You don't want BA to be in SLDZ. And now let's just construct an example in the case SL2R and SL2Z. So this really depends on how lucky you are when you think about this. You might either take a very long time or a very short time to come up with an example. But I would prefer to come up with an example of this slowly, because this will illustrate the idea how we usually construct a counterexample. You want to consider special cases where AB are both upper triangular matrices. Say A is A11, A12, 0, A22, and B is B11, B12, 0, B22. And you can compute A times B is A11, B11, A11, B12 plus A12, B22, 0, A22, B22. And B times A is a matrix. Still A11, B11, A22, B22, 0. And in upper right here, you will get A12, B11 plus A22, B12. Hope this is correct. And now, what you want is that this guy is in Z. They're all in Z. But this guy is not in Z. This is a place where you need to think a little bit harder. You want to get as many fractions as you want, but at the same time you want the product to be integers. And you want this guy to be not integers. How do you make it? So one choice, maybe you can take this to be 2 and this to be 1/2 and this to be 1/2, this to be 2. This guarantees that those A and B are in SL2R because they are upper triangular matrices and you have chosen the diagonal entries. Now A11 now here is 2 and the B22 here is 1/2. Sorry, B22 here is 2. And B12 here we choose it to be 1. A12 here we choose it to be 1/2. So this part, which is 3, is still in Z. But this part, A12 is 1/2, B11 is 1/2. Oh, this is good because 1/2 times 1/2 is 1/3. So this is very likely to be a non-integer. So, and we continue this A22 to be 1/2 and the B12 to be 1. This is very good. We got, if you calculate this, this gives you 3/4 and this part gives you 3. This part gives us 3. That's good. And the final solution is that A is taken to be 2, 1/2, 0, 1/2, and B is 1/2, 1, 0, 2. And this serves our purpose.